Hello, everyone. Welcome to the webinar series on Rate Splitting Multiple Access 2021, organized by IEEE ComSoc WTC Special Interest Group of Rate Splitting Multiple Access. This is our third webinar, and it's our great honor today to have Professor Aydin Sezgin from Ruhr University, Bochum, as our distinguished guest speaker. Professor Aydin Sezgin is also one of the vice chairs of our SIG. So let me make a brief introduction of Aydin. Aydin is now a full professor in Ruhr University, Bochum. He received his master's degree from TFH in 2000 and the PhD degree in TU Berlin in 2005. He held a postdoc position and also a lecturer in Stanford University from 2006 to 2008. Then he had a postdoc position in University of California. From 2009 to 2011, he was the head of Emmy Mueller Research Group in ULM University, and he joined the TU Darmstadt as a full professor in 2011. Aydin's research interests mainly focus on signal processing, communication, and information theory. He has published several book chapters, more than 50 journals, and co-authored one book on multi-way communication. He received the Best Poster Award at the IEEE Communication Theory Workshop and the Best Paper Award at ICC. He has served as an associate editor for IEEE Transaction on Wireless Communications from 2009 to 2014. Before Aydin's talk, I would like to remind the rules of our webinar. During the 15-minute talk, please keep yourself muted and you can type your question in the chat. After the talk, we will have a 10-minute Q&A session. You can unmute yourself to raise question, or I will choose 2 to 5 questions from the chat. Well, enjoy the talk.
The title of my talk is Rate Splitting from Fundamental Principles to Contemporary Applications. So this is a culmination of some works I have done with former PhD students, basically some while ago. Basically, we have been working on this area for some while. So we started this work with Anas Shaban, who is now assistant professor at the UBC in Canada. Sohail Gereklo, he joined Bosch in Germany. Alame, he joined Volkswagen, the car manufacturer. Basically, they are right now very interested in signal processing and machine learning. And Kevin is right now a PhD student, basically like first year PhD student. Yeah. Okay, let's get started. So here's an overview of my talk, basically. So I'm going to give a introduction on the topic, basically, like how to do resource management in modern communication networks. And this should lead basically to the motivation of rate splitting, basically, which has some nice features, basically, which can be utilized in modern communication networks. And then I'm going to apply basically rate splitting in some very elementary networks to see like the ultimate benefit of rate splitting. And once we have understood like how beneficial rate splitting could be, we are going to apply this to like more general networks, basically for 5G and beyond networks. Okay, so especially in the last part, basically, I'm just showing like how this can be applied without going into these details, just to give you an idea, basically, how powerful this is. Okay. Okay, let's get started. So what do we expect basically from a modern communication network? So we know that we have to deal with quite some traffic, basically. First of all, the number of devices which I would like to communicate, but also in the pure volume, basically, like this traffic is going to take place. And we are expecting like in terms of application services, some heterogeneity, right? So one approach basically to deal with this problem basically of allocating resources to use cloud computing, and the advantages here are that you can utilize your resources very efficiently. Basically, you have the advantage that basically the base stations are all synchronized, and then what you could do, since you have this option, basically you can do like corporate retransmission and enable due to this basically interference management. Okay, But let's zoom out, because this is just one approach basically we can do. And what I would like to do on the next slide, basically, give an overview of like general management technologies we have. So we have seen that as a system level, we can do some cloud computing, basically, which is mainly done today, like in terms of software-defined networks. On the system level, we could also incorporate intelligent reflecting surfaces, basically to improve the performance of the system, which is investigated heavily nowadays. And of course, we could apply, cooperation techniques in communication networks, basically on a network and on a system level. So in addition to this, we have also the physical layer. So the question is, what can we do basically in order to support those demands basically in physical layer? First of all, we have basically rate splitting, which I'm going to talk about today basically, and also like multiple access methods based on rate splitting, which are essentially generalization of like non-orthogonal multiple access methods basically, which have been shown to be more powerful than orthogonal multiple access schemes. And in addition to this, we could of course go for massive MIMO concepts, basically it's a physical layer, in order basically to utilize all the spatial dimensions which are available there. Okay, so let's go directly to the concept of rate splitting, and let's start with the very basic. So the conventional way basically we communicate basically is that we have basically, this is a very basic setup. We have two users, basically two transmitters here shown as base station 1 and base station 2, and they want to communicate to their respective receiver, which is given here by user 1 and receiver user 2 respectively. So assuming that there's a connection between transmitter and receiver, basically we are able to send on messages basically from transmitter to receiver. However, since we are in wireless, we usually have like interference, which is going on basically during the communication process. So that means I'm interfered at this user, I'm interfered by this base station, and I'm interfered at this user by this base station respectively. So it turns out that when looking at the optimality of this approach, which is written as TIN, treating interference as noise, we see that from an information theoretic perspective, this is in general suboptimal. Yeah. So because what we are facing here in its very basic form is an interference channel, and this interference channel, especially the capacity of it, the capacity is the highest rate we can achieve reliably over such a channel. This has been investigated since the 1980s, right? So, and still like this is like still subject to investigation. So the concept of rate splitting actually can be traced back to some early work by Carl Lane in the 1980s, 78, right? So the notion of rate splitting and the concept of common message decoding is actually first proposed a couple of years later by Han Kobayashi, yeah? And they came up with the new methods basically, which is referred to as Han Kobayashi, which is basically up to today basically the highest achievable rate we know in the interference channel. So what has happened a couple of years later, basically by Atkins, Say, and Wang, was that they have shown that a simple Han Kobayashi scheme achieves up to within 1 bit of the capacity of the interference channel. So how do you do this? So you have your scheme basically which achieves a certain rate region of the interference channel. You come up with some upper bounds, and then you look at the gap between the upper bound and lower bound. And this is what they have done, and they have shown that their bounds and their scheme is so good that there's essentially just 1 bit gap basically between upper bound and lower bound. Yeah? So that was a like fundamental step basically, and insight basically. Yet the capacity of the interference channel is still an open problem basically. It's I think one of the most challenging problems we have in communication. Yeah. Good. So how can we incorporate rate splitting? What is the idea basically? So what's happening is actually that let's look back at the figure we had before. Basically, what the users are doing, or the base stations in this case, they are splitting their information in 2 parts. Yeah. So the first part is given as with a superindex P, and the other part is given as like with the superindex C. P stands for private and C stands for common. Yeah? And the idea is basically that the users are splitting this information into two parts, giving the receivers more degrees of freedom, basically, how to deal with those signals. So they, for instance, this user could decide to, decode like this common message first, and then move on and decode the common message of this user, and then he might basically continue with decoding his own private message, while usually we ignore the private message of the other users. Okay, so that's the general idea. So we are splitting the messages basically into multiple parts, encode them separately basically, and sense the superposition of those signals, with the advantage that I give the receiver more freedom basically to decide how to proceed with the decoding. So again, we have interference basically also in this case. So but here basically, we have some structure in the interference which we can utilize. Okay? So that's the basic concept of rate splitting, and let's see basically how they are beneficial in elemental networks. And here I'm going to consider like two elemental networks. First, the two-way relay channel, because I think this is going to be one of like a type of network which is going to be very relevant for 6G. And then I'm going to extend this basically to more users and look at the interference relay channel. And again, afterwards, we are going to generalize it more and look for more complicated networks. Okay, let's get started. So there has been some work basically, after, this nice insights how rate splitting is beneficial. For instance, there has been some work basically on like interference channels in general, basically, and how rate splitting can be used in order to improve this. There has been also some work on the interference relay channel, which I'm going to like briefly discuss about. And also like, multi-way channels. So here, this is like, like a picture showing a two-way relay channel. There has been also some work on multi-cell wireless networks and like the benefits basically of rate splitting applied there. Yeah. And also basically, there has been some work on multiple input, single output broadcast channels, so MISO channels, MISO broadcast channels by some groups basically, showing the benefits of rate splitting there as well. Yeah. So here are some references basically for your convenience. You can look them up basically. Yeah. Okay, let's start with the two-way relay channel. So the two-way relay channel was a like channel which was proposed and first studied by Rankov and Whitney in 2006. And the idea is as follows. So we have two users which would like to communicate with each other. However, there is no direct link, so the direct link is very weak, so we ignore it. So the only way they communicate is via a relay, which is shown here in the middle. Yeah. So how do we proceed here? So assuming that we have a Gaussian channel, that means that we have additive Gaussian noise. Basically, we have, like three inputs. We have the input from user 1, x1. We have the input from user 2, x2. We have the input from the relay given by XR, and then we have the powers accordingly, P1, P2, and PR. Okay, so here again is the setup basically shown in a different way, basically, and then also showing the noises. Right? So the output basically of the receiver, or sorry, at the relay is, when the nodes are communicating to the relay is like this. So we have YR is equal to X1 plus X2. So we get the superposition of the two transmit signals plus noise, while the signals at the individual users are given by yi equal to xr, so the signal from the relay plus the noise. Yeah. So you see, we don't have since we don't have a direct channel basically between the nodes, basically we are only seeing the transmit signal of the relay. So there's no like additional component from the other node respectively. So what we can do now is basically try to look at the capacity region of this setups. We have two users, so therefore we have to deal with the capacity region. And we would like to see at the end of the, of this part, basically how rate splitting is beneficial here. Okay. So the first approach here, you can apply basically in this two-way channels, since you have two stages. The first stage is you communicate from the nodes to the relay, and then the second stage is you communicate from the relay back to the nodes. You could consider them as separately, and that means from the nodes to the relays we have a MAC, and then from the relay to the nodes we have a broadcast channel, right? And then since the capacity of those two networks basically is known, then we can write immediately rates. So for the MAC we have those two expressions here basically for the individual rates and for the sum rate. And then basically when we basically receive those signals, we have decoded them at the relay. Now we are able to send them back or forward them to the nodes, and the rates are then constrained by this expressions here. Okay, and what you get basically are two regions. The blue region is given by the MAC constraints here, and this red region is given by the broadcast constraints, right? That means since I'm decoding at the receiver, the overall performance is given by the intersection of those two regimes. And this regime we refer to as decode and forward inner bound, because we decide to decode the signals or the individual components x1 and x1, and then try to basically process them in the next step. Okay, so the cut set bound, which is basically an upper bound, is shown here, and you see that basically the cut set bound is quite far away from this lower bound, right? So we know that the cut and set bound is in general not very tight basically, but it's a very simple bound. As you can see, it's very convenient here basically, and we see that there's a huge gap basically between this outer bound and this inner bound, right? Yeah, so the question is basically can I improve upon this rate by coming up with better schemes? We are not going to basically look at how to derive outer bounds. We are going to stick to the cut set bound. It's going to be just fine for us here. So how can we do better than this? Yeah. So let's look at the sum rate. So which is going to be like 1 point basically on this capacity region, right? So we simplify the assumptions. We set all the powers equal. We noise variances are all equal to set to 1. And in that case, the MAC, expression reduces to this very simple expression. Okay. Similarly, the broadcast expression reduces only to this, to this component here. Yeah. So now, if you look at the sum rate, basically, and then look at the gap between the cut set bound and the inner bound we had based on degrees of freedom, we see that for lower SNR we might be okay, but as the SNR goes higher, there's a huge gap, right? So we would like to improve upon this. So now basically the idea of how to improve it is, we could use network coding. So the idea would be that I'm still going ahead and decoding those signals x1, x1, x2 separately, but now I'm basically, once they are decoded, I'm calculating at the relay a new message which is given by MR, and MR is basically the XOR combination of the signals I have, of the messages I have decoded, right? Now basically what I do is I take this XOR message and I encode this message and send this data basically now back to the users in this form. So I'm designing a code word XR based on this message MR, and I'm going to send this, and basically the rate basically then is given by the maximum of R1 and R2. So now, since basically each node knows what it has sent by itself, it can decode now XR. That means it will get MR and then apply another basically XOR modulo operation to get the desired information, right? So both of the nodes do this basically. That means node 1 knows M1, does this operation to get M2, and node 2 basically now knows M2, does this operation to get M1. Yeah. So that means the rate in the basically from the relay to the nodes is then given by this expression, right? That means the sum rate is going to be twice this, which is going to be like this. Yeah. So that means we have improved a bit. And this is illustrated here. So we have improved upon the decode and forward method. Okay. So you see that it's doing well at lower scenario, but it's still bad basically at very high scenario. So what can we do now? So one important insight is that actually we don't need to decode the message as its relay, right? There's no need, right? So the concept of the relay is just that it should support the communication. How it does it doesn't matter, right? So in order to understand the next concept, so let's look at the binary additive noise channel. So that means the input signals are basically from field 2 basically, and the outputs are then basically nothing else than the XOR combination of the input signals, while in the downlink basically the output signal is just what I sent from the relay. Yeah, so I don't have any noise, right? So now what we can do is that the relay decodes basically x1 and x2, right? And then constructs basically based on this signal, right? Yeah. So that means basically in the binary additive noise channels, basically the relay alternatively basically could decode basically XOR directly, because we are getting, recall that in the idea of network coding is that you are able basically to construct this position, but then since the channel is doing this automatically, we can just try to decode basically the XOR combination of those two instead of trying to decode each of them separately, right? So that means we are getting this one signal basically which we try to decode, and then we try basically to send this back to the receivers, and everything is going to be fine, right? So that works fine in the binary noiseless channel, but the question is, like physical channels are unfortunately not noiseless and they're not binary. So what can we do, right? So usually in physical channels, we use Gaussian channels as, as a good representation of physical channels, right? And there basically it was shown by Shannon basically that random codes are the best we can go for, right? The problem is with Gaussian code words is that the sum of two code words is not necessarily a code word, right? So that means we are not able basically to reproduce what we have done in the binary additive noiseless channel in the Gaussian channel if we go for Gaussian code words. So now what? So what we can do is you use a concept of computation. Yeah. So what does computation say? What does it mean? The computation is essentially the process of recovering a function instead of individual components of transmit code words. In our case, the XOR combination from a received signal. Yeah. And then basically those signals have been sent over the channel, right? So the channel basically has done some computation. So it provides us a function of code words, and we try to compute this function. So how is this done basically in physical channels? So this can be done by lattice code. So as an alternative to Gaussian codes, we use lattice codes, because lattice codes have the advantage that the codes are located on a grid. That means the sum also is also located on a grid. Yeah. So when we do this, basically we get those this expression here, which you see at the bottom. Those are the two expressions we got before. And if you look at the plot, you see that we have fundamentally improved basically. This is a green curve basically in comparison to network coding and decoding forward, right? And the main reason is that we don't try to decode anything basically individually at the relay. Okay. Good. So we significantly improved basically. I mean, not so good at lowest scenario, but very good at highest scenarios. That means we could actually do a combination of network coding and compute and forward, right? So let's move on. So if we now apply this to the rate region, then this is how it looks like. You see that's decode and forward. That's network coding, and this is what we get from compute and forward. Now, as I mentioned, we can do a combination of network coding and compute and forward. And then we will basically get this purple region, basically, which is basically obtained by time sharing between network coding and compute and forward. So the question is, so we have simplified this analysis, looked at the case where all the powers are equal. Now what happens if we move on to arbitrary powers, right? So here's where basically rate splitting comes into play. So what's happening is actually that we reduce, assuming that P1 is larger than P2, we reduce P1 to P2 and use compute and forward, and then basically we get this, right? So the question is, can we do better than this? Yes, we can, because what we can do is now, we have reduced the power from node 1, but we can like the safe power we can use to send an additional signal. So what we do at node 1, which has higher power than node 2, is we can send this signal 1, which is referred to as C, with the index C, and then on top of this we send another signal D, basically, right? So we essentially send the superposition, basically, right? So essentially we apply rate splitting. The second user, which has basically lower power, he just sends one signal. So what's happening now is, those are the constraints we have on the powers. Basically, the relay receives the superposition of 3 signals, basically, 1, 2, 3. And you see that we have written this in this way, basically. So this is basically the message C from transmitter 1. This is message C from transmitter 2. And now we can apply the concept of compute and forward, and first apply basically this first message here. So we are really decoding this part, right? And then we try to basically decode the combinations, the superposition of those 2 signals. Yeah, assuming that they are lattice decoded. By doing so, basically we get for RD, for this part we are getting this rate, and for RC basically we are getting this rate here. Yeah. So then what's happening now is that the relay basically, after decoding those 2 components, it forwards XRD basically, and this, like this lattice coded XRC. This is the power we assume basically, and then the nodes basically receive the superposition of 2 signals. And what they do is they first decode basically, this, and then they extract the desired compute and forward part, and then they proceed and decode basically XRD. By doing so, this is what the rates are they get, and this is the overall rate regime basically, which is significantly higher than basically what we would do without basically the rate splitting. And it turned out basically that if you do this, you can show that this region basically is a constant gap away from the cut set bound, basically, right? That means constant means I'm independent of the power used, basically, right? So this is just due to the use of rate splitting. So here we see the benefits of rate splitting. Without rate splitting, there might be other methods, of course, but without rate splitting, we're not able to get this constant gap. So that's basically one elementary network. Now let's basically try to generalize what actually happens if you have more than, like those 2 users and you are suffering from interference, right? So again, you could basically, go for a relay, which helps you in this process. So we are ending up in a so-called interference relay channel. Yeah. So this is again the conceptual perspective of it, basically. And to simplify, basically what I have done is some of the channels basically are identical. So all the direct channels are given by HD, basically. So it's a symmetric channel, basically. Yeah. So what can the relay do? So how can we improve this? So what we do here, basically, we don't look at the capacity. What we rather do is we look at the first order approximation of the capacity, which is referred to as the degrees of freedom. In particular, we look at the generalized degrees of freedom, in which we try to parameterize the channels, the direct channels, and the channels through the relay. So that means in the most general setup, the approximation to the capacity is given by GDF, which is essentially determined like this. So you have the capacity, you normalize this, and then you'll try to basically let the SNR grows to very high values, and then basically try to get an impression how this network behaves asymptotically. So this is essentially a stepping stone, basically. So you first analyze the degrees of freedom, then look at the generalized degrees of freedom, which we are looking now, basically, and then you, based on the insights, you try to get an output in terms of the exact capacity. So so now let's look at this degrees of freedom, basically generalized degrees of freedom of this interference relay channel. What is shown here is the generalized degrees of freedom, basically for the basic interference channel, which I've illustrated at the very beginning. So there's no relay, just to transmit it to receivers, and they interfere with each other. So what we get is this very famous Atkins-1 W curve. So and alpha essentially is a parameter indicating the strength of the interference. alpha equal to 0 means the interference is 0, so there's no interference. Alpha equal to 1 means basically is that logarithmically, basically the desired signal is as strong as the interference channel signal, or to put it in other words, the interference signal is as strong as a desired signal, and as alpha is getting larger basically than 1, basically the interference is getting higher and higher. So what we see is that the degrees of the general degrees of freedom decreases first as alpha increases, and from a certain point on basically it increases again, decreases again, and then increases and then stays constant. Yeah, the main reason why it improves here again is because of rate splitting. Yeah, so this is applied here as well. But what we would like to do is we would like to look at the interference relay channel, and for the interference relay channel basically we would like to look at this regime, which is more interesting. So, and when you look at this, you see basically that similarly to this behavior, basically you first improve, and then basically you decrease. Suddenly basically your performance is not improved as much, so you're losing essentially in terms of degrees of freedom, and then you stay constant, and then increases again, and then it gets constant. Yeah, so it's a very like different behavior compared to the interference channels, where from this point on it was like monotonically behaving, right? So what is the approach we apply here? And so I would like to concentrate on this region here, and given the time constraint, I would like to move on a bit faster. So this is a complete characterization of the generalized degrees of freedom of the interference channel basically. So let's move on. So we would like to look at a scenario where basically we look at this regime. So that means the relay is going to have a better observation basically than the receivers. Okay, so what do we do? So here is the concept of rate splitting. So I would like to illustrate this here, and I don't want to go into detail, but essentially what you do is, it's a transmitter 1, you split your message in 2 components, in yellow and green. At the transmitter 2, you split your message in 3 components, yellow, green, and this gray area. Okay, so now you send this data basically to your relay, and what the relay is going to get is basically the superposition of those 2 signals, right? So essentially, since it's a superposition, we are going to get this yellow, this green, and this gray signal. Okay, so now basically assuming that the relay knows this green part, which is which it knows because you apply basically Gauss-Markov encoding. Assuming that we know this, we can subtract this from the received signal, end up in this signal here. Then we can basically decode the gray signal, and then decode the relay signal green. I mean the yellow signal. That's a relay. Yeah? So in the next channel used, due to this Gauss-Markov encoding, basically this yellow one turns out to be the green one, because what we do is basically at the transmitters we send this signals again, but at a different level. Yeah, so that means basically now with the next stage, basically since I have decoded yellow in this stage, I know it basically in the next stage, right? Yeah, so essentially we are creating some kind of a cognitive relay, basically, right? So you see we have used like rate splitting. We have split the messages basically into multiple components. So now basically what the relay does is basically, so it knows the green component basically, and now the gray part basically, and essentially so what we see here basically is with perspective at the receivers basically. So they observe again a superposition in this way basically. Now the relay is sending also a signal in this way basically. So you see that now we have like superposition of multiple signals. The user is now decoding the gray part first, right? It's moved on here, so we are decoding basically the gray part first, and then basically since we know the gray part, we can remove it from here basically. Yeah, and then since we know the green part, is we can remove it from here as well, basically, and successfully, basically, you can decode the individual messages. Right? So by doing so, basically, so let me move on, basically. So we essentially are able to do so splittings, basically, which enable us basically to neutralize interference. So what we can do is basically we can send signals from the relay in such a way towards the receiver such they can cancel transmit signals coming from here. Yeah, so we neutralize over the air basically some signals, right? Yeah. So this is the way how you get basically this improvement for the relay channel. I'm not going to get into details for the other regions, but again, you apply some kind of rate splitting basically and enable some flexibility at the receivers basically. And because of this, basically, you are able basically to get such a region basically, which is a strict improvement in comparison to an interference channel. Yeah. Good. Let's move on to more general networks. So let me move on a bit quicker, basically. So let's skip this. So here again, we apply the concept of rate splitting, basically. So each message is split into two parts, basically one common message and one private message. And basically, we apply this method which we have used based on elemental networks to more general networks. Yeah? So the problem is when we move to those like general networks, for instance, cloud radio networks, then there are a couple of challenges which we didn't have in those elemental networks. The first challenge is that we have to determine the common message set for each user, because the common message set is the one which is decoded by all the users. Right? Then another component which we did have so far is that we have front-end links which are of limited capacity, right? We have to deal with this as well. And finally, the rates we have to deal with, they are usually non-convex, and therefore, both the objective and the constraints are non-convex, and we have to deal with this as well. Yeah. So the experimental setup we have looked at is given here. So we have 7 cells basically, which are wrapped around and connected to cloud. Yeah. So we have basically done some simulations based on this. Basically, here are some parameters chosen basically. And what is shown here is basically the achievable sum rate as a function of the number of users in the network. And what we see here is, first of all, treating interference as noise, so no rate splitting. And here, basically, the improvement by using rate splitting and successive interference cancellation at the users. You see that we have a significant gain basically in terms of rate, right? So changing the objective. So if you want to improve upon the transmit power, so which we have looked at as well, basically, and here on the axis you have like the minimum quality of service constraints you have to fulfill for the users. Then we see basically that this is basically what we are able to provide with TIN. And if we basically use rate splitting, then we can improve significantly in comparison basically to treating interference as noise. So because what does it mean? We are essentially able to use the same power. We are not basically losing much in terms of power basically, and still we are more power efficiently basically, because we are using less power basically by using rate splitting in comparison to TIN by providing the same quality of service. Yeah. So here are just some values basically in which you can see basically that since it's like a feasibility problem basically, that with rate splitting basically we are able to achieve feasibility in a lot of cases basically where like treating interference as noise basically fails to provide those quality of service constraints. Yeah. So especially if basically the minimum rate basically is getting higher and higher, you see that there's a significant gap between basically rate splitting and treating interference as noise. Yeah. So what we have looked at here is again another objective basically, this time the energy efficiency. And here basically you see that this is basically like that we have two like different approaches basically, but what you should get from this picture is if you go for treating interference as noise, basically this is the gain you have. Now basically if you go for rate splitting basically, then this is the improvement basically shown with those gray arrows basically, how much you can get better, right? So the discussion about this GO basically is essentially how you do the optimization, but this is not relevant at this point. So now let's basically look at what happens actually if I include intelligent reflecting surfaces, right? Which is like a hot topic nowadays. So reflecting surfaces have the advantage basically that they can improve upon the network, right? So what we just need is basically, a way to control basically how they reflect the incoming signals, right? The issue is that, by deploying such a network that at certain receivers, we might be able to improve basically the signal quality by reducing basically maybe, the interference. But at certain other users, it might be that I'm doing a bad job because, I'm supporting this receiver, but I'm harming the other users, right? So that means, we have to do some very sophisticated interference management basically, right? Because otherwise we are improving the life of one, but harming the others, right? So what we have done is basically, we have tried to model basically the IRS basically as a passive object basically, where you can basically, play essentially with the amplitude, with the phase, frequency, polarization. And given basic some assumptions, basically, we have looked at this scenario basically again using rate splitting, and let me just show you the result. So what you see here is essentially basically first treating interference as noise, first without IRS and then with the IRS, and then here is rate splitting without the IRS and basically without the IRS, right? So you see basically that basically we are again significantly improving in terms of using rate splitting. So what is shown here is again the energy efficiency as a function of the frontal capacity. And what I would like to highlight here is that you see that here is a benefit what we get basically by changing from treating interference as noise to rate splitting. Here in this case we don't have the IRS involved. Now if you move basically from tin to and include the IRS, and this is improvement you get by using the IRS. And now again, when you switch from the treating interference as noise to rate splitting, then you are going to get this improvement. And the interesting aspect is you see that we have some basically synergetic gains, because you see that the gains here are this large and the gains here are a bit higher. So we are getting basically 24% more gain basically by combining rate splitting and IRS, because there's a synergistic benefit in both cases. Yeah. So we can apply those concepts also to not only to cloud but also to edge networks basically, especially if you want to improve upon the latency. Then you should have caches, local caches at the nodes basically. So to apply basically caching at the physical layer. And this is what we have done as well basically. And it turns out basically also in this case, let me just given the time basically, let me just move on. So this is the setup we looked at first basically. So you have a node which has a cache basically, again finite limited capacity basically, and you want to support these users. And it turns out basically that in order to basically provide the best basically, you can again use some synergistic benefit of caching and rate splitting and apply, let me move on basically to apply rate splitting basically to get the overall best performance basically, right? In terms of here we looked at latencies, this is what you're improving upon. Yeah. So here just to illustrate basically that again basically we are using rate splitting. So ignore the figure for now. Essentially what we do is basically we use a combination of common signals, private signals, and so-called interference neutralization signals. Right. So again, we are doing rate splitting now. Instead of 2 components, we have 3 components basically. And by doing so, we can do much better than without basically. Right. Same setup can be applied for such a channel. So we have now a cache-aided relay channel basically, where the relay has some local cache. And again, basically by applying some rate splitting basically shown here, basically here we use a combination of common and private signaling. You are able to improve the system performance basically. Yeah. This actually is also my final slide. Basically, with this, I would like to conclude my talk. Basically, again, I tried to give you an overview basically of the application of rate splitting, starting from the basic concepts basically, and showing you the benefits of it also for larger networks. thank you very much for attending the talk, and I'm happy to take your questions.
Thank you, Aydin, for interesting talk. So, can you hear me now?
Yes, perfect.
Okay, great. So, any question from the audience? Well, actually, I have one question on the IRS application. So for the results that you illustrated in the IRS application, I would like to know the number of IRS elements are there, and whether you consider like discrete phases for IRS, or you consider continuous phases for IRS.
What we have looked actually is we kept the number of elements like variable, so that was basically, so it was not fixed basically, and we kept the like you know, like general, and then basically we investigated the impact of the dimension of the IRS basically on the performance of the system. So yeah, so that was those were system parameters basically, and there's an interesting basically like interplay basically, depending on the dimension of the IRS basically, you know, you have to design your rate splitting approach basically accordingly basically. So regarding the assumptions on phase and so on, we actually looked at like discrete case, yeah, but also like to, you know, to get an upper bound basically, we also looked at the case where basically you have like a continuous like the continuous phase basically. Yeah.
Okay, I see. So is there any, okay, so, okay, so for the question, so you will find the slides. So there's one question from Marco, but it's not related to the talk. And then you can find the slides from our RSMA webinar after the end of the talk, okay? And any other question related to the talk?
I have a question. I wonder, when you implement this RS system, did you consider about how the RS phase will somehow influence the channel? I mean, did you model the phase shift into the channel? That's my question.
The whole question.
Hi, can you hear me?
Yes, I guess the question is that can you give any insights on the number of IRS elements that will influence the performance of RSMA compared with team?
Yep.
Am I correct?
Yeah.
Sorry, everybody. I think I somehow was kicked out basically of the meeting, so I didn't get the question. Would you be so kind as to repeat the question?
Let me.
Okay.
Go ahead.
I mean, when you implement the RS system, did you consider about how to model the phase shift of the RS system into the channel? I mean, because actually, when you use RS, you want to somehow increase the actual power that the receiver can get. So the RS will somehow change, or somehow change a little bit about the channel gain or the channel shift. I mean, when you implement, did you consider about this part?
I mean, by implementing, you mean, you know, simulations, right?
Yeah.
Okay. So I mean, the way we simulated this, you know, is shown here essentially, right? So we assumed basically that we have passive IRS basically. That means we have this constraint basically, you know, and that means we have two parameters to play with, basically, which is basic beta R and constraints we had basically, right? And this is what we have implemented. And I'm not sure whether this answers your question, but this is the way how we implement this.
Because I wonder that if we somehow treat the channel gain as a constant, then actually it's a little bit different from you treat the phase shift of RS as a part of the channel gain. I mean, in my opinion, it's a little bit different.
I'm really sorry. I'm getting information that my internet connection is unstable. Would you be so kind as repeat? I don't know what's happening, but I think
no worries, no worries. I mean, actually, in my opinion, if you treat the channel as a constant, then actually it is different from you treat the phase shift of RS as a part of the channel gain.
Okay, I think you're like what you say is that if I incorporate the one way basically to deal with the IRS is to incorporate it in the channel mode, right? To be a part of it, right?
Yeah. That's what I mean. Yeah.
And you're saying that this might be not the correct approach, basically to proceed, or is this what you're saying, or?
Yeah, I mean, maybe there are different ways to see how the RF will improve our whole system. Yeah. So I guess your way maybe treat the channel gain as a constant currently, right?
Mm-hmm.
I mean, if we treat the phase shift as a parameter of the channel gain, then also you put this part into the RSMA design, we will also get some benefit, not a simple combination between these two parts.
Okay, you're saying that you might get like synergistic benefits there as well, basically, right? Again, as I mentioned, just the combination of those two seems to basically they seem to benefit from each other, and right? Yeah, there might be indeed other synergistic benefits of IRS and other concepts, Vicky. That.
Thank you.
Sure.
Okay, so I think this is the end of this talk. Thank you, Aydin, for a very comprehensive talk. And if the audience have any other questions, you can send. Okay, so we have another question. Well, I think maybe adding this will be our last question. Okay. And there's one question in the chat, and the question is that can the private messages or common messages of users be served by several base stations cooperatively in CRAN, like COMP, or just serve the private and the common message in different base stations? Thank you.
Okay, yeah, very nice question. Actually, yes, I mean, this is what you can do, right? I mean, you have the freedom basically to send. Basically, let me try to illustrate here. So what you can do is basically you can decide basically to send like one common message basically from multiple base stations, or you can decide to send different common messages from all the base stations. This is the design of freedom you have basically, right? And it turns out that in some cases, indeed better basically depending on the frontal link basically to send all base stations, and so there's an interplay between the frontal constraint basically and also you choose and allocate the common and the private messages to the individual base stations. Yeah. Look at this basically. It's the impact is quite the designs. I'm lost again.
Thank you, Aydin. I guess I'm lost. I don't know whether that's the issue from my side. Well, so I have to end this talk as soon as possible. Otherwise, I don't know what else network issue that will happen. And I would like to remind all for our next webinar on next Tuesday, given by Professor Pei Xiao from Surrey University. You can go to our webinar website for more information. Okay, thank you all for attending this talk. Bye-bye.
Thank you, everybody. Bye.